1, the intersection of a line with a plane and the intersection of two lines. So in this section, we're going to be talking about two different things here. Okay, so first we're going to be talking about the intersection of a line with a plane. There's three different scenarios that we can end up with. So case one is we have one point of intersection. So what we have is we have a line and it goes through a plane and it intersects that plane at one point. We call that point P. Okay, we call a line L and we call a plane pi. Just as a recap. So case two, 0 points of intersection. So the line here is parallel to the plane. So there's no points of intersection. Okay, if you take a look at this diagram right here, the diagram highlights the normal. So what would we do with the normal? Well, the normal of this line is probably going to also be perpendicular to the plane. So keep that in mind. Okay, and then case three, infinite points of intersection. This is when the line actually is contained in the plane. Okay, so the plane contains the line. So every single point on this line also lies on the plane. Okay, example one, determine the points of intersection between this line L, okay, and this plane, pi. So first what we want to do is we want to convert the line, the equation of the line, which is right now in vector form, into parametric form. So let's go ahead and write x equals, and we have 3, 1, 2 through 3, 1, 2, and then 1s, negative 4s, and negative 8s. Okay, so these are the parametric equations of the line. So by subbing in these parametric equations, what we're saying is, when does this line equal this? When is this line in this plane? Okay, so let's go ahead and do that. So let's take the equation of the plane, 4x plus 2y minus z minus 8 equals 0. And for the x, let's sub in 3 plus s. For the y, let's sub in 1 minus 4s. And for the z, let's sub in 2 minus 8s. And this is very convenient because now we have one equation and only one variable. So our variable is s. So what we're going to do is expand and solve for s. Okay? So we have 12 plus 4s. We have 2 minus 8s. Then we have minus 2 plus 8s. Minus 8 equals 0. Okay, this positive 2 and this negative 2 cancel out. This negative 8s and this positive 8s cancel out. So right now we have, what's 12 minus 8? I get 4 plus 4s equals 0. Bring that over. 4s equals negative 4. And I get s equals 4. So, sorry, s equals negative 1. So what we have here is s equals negative 1 is telling us that with the parameter, subbing in the parameter s equals negative 1, we're going to be able to find a point, like the point of intersection. So let's go ahead and do that. Let's switch colors, okay? So x equals 3 plus negative 1. So our x value is 2. Our y value, it's going to be 1 plus 4, which is 5. And our z value is 2 minus 8, negative 1. So this is 2 plus 8 equals 10. So I get, there is one point of intersection at the point 2, 5, 10. To determine the points of intersection between this line, L, and this plane, pi. Okay, so L's already written with parametric equations. What I'm going to do is actually write those down the page. I find them much easier to follow. So we have 2 plus 2t and then 9 plus 8t. Okay, haven't done anything, just rewrote the equation of this line. So just like in example 1, let's go ahead and sub in these expressions for the x, y, and z into the Cartesian equation for the plane. Okay, so we have 2 plus t minus 5, 2 plus 2t minus 6, plus 9 plus 8t minus 6 equals 0. So let's go ahead and expand and simplify, okay? So we have 4 plus 2t minus 10 minus 10t plus 9 plus 8t minus 6 equals 0. Okay, we get 2t minus 10t plus 8t, it's actually 0t, okay? And 4 minus 10 is negative 6, minus another 6 is negative 12, but then plus 9, I get minus 3. So let's just bring that over. I get 0t equals 3. Okay, so at this point, you're going to see a lot of this throughout this this unit. Okay, 0t equals 3. So what number can we sub in for t so that 0 times any number equals 3? Well, 0t is never going to equal 3. What this means is that there is no solution. Okay, we can't multiply any number by 0 and it equal 3. It would be equaling 0. Okay, so this is the first method. This is method 1. Okay, now what I'm going to do is I'm going to show you another method. So I kind of mentioned this in the first screen. If a line and a plane are parallel, so no solution, they're parallel, of course, okay? If a line and a plane are parallel, then the normal to that line is also going to be the normal to the plane, okay? So what that means, or the normal to the plane is going to be the normal to the line, okay? It's going to be the exact same thing. And what that means is that the dot product is going to equal 0. So we can go ahead and take the normal from the equation of the plane to negative 5, 1. Okay, so let's go to negative 5, 1. And what we're going to do is we're going to take the dot product of it, okay, against the direction vector of the line, 1, 2, and 8. 1, 2, and 8. So 2 times 1 is 2, plus negative 5 times 2 is negative 10, plus 1 times 8 is 8. We get 0, okay? Therefore, the normal of the plane is perpendicular to the direction vector of the line, okay? Therefore, no solution. And that's an alternative way to show it. Example 3. So same type of example, determine the points of intersection between this line and this plane. Okay, so I'm going to rewrite the line as x, y, and z in the parametric equations for this line. 3, negative 2, 1, plus 14s, minus 5s, minus 3s. And then now what I'm going to do is sub these into the equation for the plane. So we have 3 plus 14s plus negative 2 minus 5s plus 3, 1 minus 3s. Sorry, I'm going to just carry on right here, bad math form. Okay, so we have, let's just expand this one, okay? And then let's just rewrite it without brackets. 3 plus 14s minus 2 minus 5s plus 3 minus 9s minus 4 equals 0. Okay, 14 minus 5 minus 9, I get 0s. 3 plus 3 minus 2 minus 4, I get plus 0 equals 0. In other words, we can rewrite this as 0s equals 0. Okay, a little bit similar to the last one. Last time, and I'm just going to put this at the side of the paper, we had 0t equals some number, which will never happen, right? But in this case, what number can we sub in for s so that 0 times that number equals 0? Well, any number. right? So what this means in this case, when we get 0s equals 0, and we can sub any number into s, this means that there are infinite solutions. This means that the line lies right on the plane, okay? The line lies on the plane. And every single point on this line is a point of intersection. Example 4, determine the points where this line and this plane intersect, if any exist. Okay, I'm just going to write the line down the page. So x equals 2 minus s, negative 1 plus 3s, and z is 4 minus 5s. Okay, so this plane looks a little bit different because for this plane, the y and the z components are both 0. So we have x equals negative 3. Well, this is a little bit easy because this takes us back to like grade 9 or grade 10 where we do substitution. So what we're going to do is we're going to go ahead and substitute 2 minus s where that x is. Okay, so I get 2 minus s equals negative 3. I'm going to bring this s over, bring that 3 over. I get 5 equals s. Okay, so this we know for sure because we equated x equals x. Two expressions or two equations that are equivalent to x. Now all we want to do is substitute that 5 into the y and substitute that 5 into the z to find the other two coordinate points. Y equals negative 1 plus 3s. Okay, so negative 1 plus 15, I get 14. And z equals 4 minus 5s, which is 5. 4 minus 25, I get negative 21. So I get, therefore, the point of intersection is negative 3. Don't put 5. X equals negative 3. It already tells us that. Okay? 14, comma, negative 21. All right, and here's the second topic, the intersection of two lines. Okay, so there are different cases here. So if we do actually have intersecting lines, we have two cases. We have one point of intersection or infinite points of intersection. So as a recall, and this is from grade 9, okay? As a recall, one point of intersection, the lines are not parallel and intersect at a single point. Whereas infinite points of intersection, the lines are coincident. What this means is that they lie on top of one another, okay? They're identical. They have an infinite number of points of intersection, okay? Every single point on the line is shared with every single point on the second line. All right, now non-intersecting lines. If we have non-intersecting lines, what this means is that there's either going to be 0 points of intersection or 0 points of intersection. One's going to be parallel and distinct. We've seen this. Okay, so up until here, this should be kind of a review. We're just going to have a little bit of a different approach since we're doing calculus. And the two lines are parallel and distinct, so there's no points of intersection. Okay, if you remember from grade 9, they would have the same slope, or in this case, in vectors, they have the same direction vector. Okay, but then they would have like a different, say, x-intercept or y-intercept or z-intercept in this case. Okay, this is where we see something new. 0 points of intersection, the lines can be skewed. What this means is that the two lines are not parallel, but so you can't really tell by the direction vectors, but there's no points of intersection anyways. Skew lines only exist in r cubed. They don't exist in r squared. Okay, and all this means is that they just lie on a completely different plane. So even though they're not parallel, they still won't intersect. For line 1 and line 2, so line 1 and line 2, determine points of intersection if any exist. Okay, so I'm going to rewrite both of these in the form, in parametric equation form. Okay, negative 3, 1, 4 minus s plus 4s. Okay, and then we have XYZ again. We have 146 minus 6t this time. Okay, whenever we write two equations, we always have to have a different parameter. Okay, one parameter that's unique for each. Okay, so here are the two lines. Now we want to know if they intersect. First of all, let's test. So let's go direction vector 1. What's direction vector 1? Negative 1, 1, 4. Okay, and direction vector number 2, we get negative 6, negative 1, and 6. So direction vector 1 is not a multiple of direction vector 2. Okay, since they're not a multiple, what's not going to happen is they're not going to be parallel. And then they're not going to have infinite number of, so this would be no points of intersection, parallel and distinct. Okay, and they're not going to lay on top of each other and have infinite. Okay, the two cases that we're going to be looking at is, are they skewed, or do they have one point of intersection? Okay, that's what we're going to be looking at. Now, all we have to do is take one of these, say the x's, and let's equate them. Okay, so we're going to have the equation negative 3 minus s equals 1 minus 6t. And then what we can do is we can equate the y's. So then we also have 1 plus s equals 4 minus t. So let's go ahead and move these around. Okay, so we have negative 3 minus s minus 1 plus 6t equals 0. Minus 3 minus 1 is negative 4. Okay, do the same for this equation. 1 plus s, we'll bring over the 4, so negative 4 plus t equals 0. And let's put these in the same order. So negative 4 minus s, so constant s and then t. So 1 minus 4, so constant s and then t. What we have to do is we have two equations and two unknowns. We can either use substitution or elimination. So I set these up so that I can use substitution. Oh, sorry, elimination. So I'm going to stack them on top of one another. Okay, negative 3 plus s plus t equals 0. Okay, I have a negative s and a plus s. Because these are opposite signs already, I'm going to add the equations. So negative 4 plus negative 3 is negative 7. These s's will cancel, and then I get plus 7t. Bring that 7 over, I get 7t equals 7, so t equals 1. Okay, so the parameter t equals 1. Let's sub that 1 back into this equation, and it doesn't matter if you want to sub it into equation 1 or equation 2. You'll get the same answer. Okay, so let's sub that in. Negative 3 plus 1, I get negative 2. Bring that over, I get s equals 2. So now I have the two parameters, t equals 1 and s equals 2. At this point, what we want to do is we want to sub these two parameters back into the original equations, and we want to make sure that we come up with the with the same point. Okay, if we sub these two parameters back into these parametric equations and we come up with different points, then they would be skewed. So let's see if we come up with the same points. So x equals negative 3 minus 2. So x equals negative 5. And then we have x equals 1 minus 6t. So 1 minus 6 is negative 5. So x equals negative 5, we get the same thing. Now let's see what we get for the y's. Y equals 1 plus s, which is 3. Then we have y equals 4 minus t, which is also 3. Okay, so that one works as well. Now let's test the z's. Z equals 4 plus 4s. So 4 plus 8, I get 12. And then I get z equals 6 plus 6, 1, which is 12. So because all of these line up, therefore, the point of intersection is -5, 3, 12. Okay, example 6, we have a similar to example as the last one. So again, I'm going to stack x, y, and z. We have -1 plus s, 3 plus 4s, and 6 plus 5s. So that's L1 and y, x, y, and z. Okay, again, we're going to have a different parameter, so you're going to be able to tell everything, every equation with a t in it is going to be from line 2 because that's the parameter of line 2. Okay, here we go. All right, so take any two of these and equate them. I don't even look, I just do x and y. Okay, so let's go ahead and go -1 plus 5 plus s. I usually put s's like that, equals 4 minus t. Okay, -1 minus 4 plus s plus t equals 0. So I get -5 plus s plus t equals 0. Now let's do the same thing for the y's. 3 plus 4s equals 17 plus 2t. So 3 minus 17, I get -14 plus 4s equals 2t. Oh, let's go minus 2t equals 0. Okay, it doesn't matter. So for this one, because the s's and the t's are not multiples of one another, I'm actually just going to use substitution. So I'm going to isolate s. I'm going to bring over the 5, so 5 minus t. I'm going to substitute that in to this equation where the s is. -14 plus 4, 5 minus t minus 2t equals 0. And this is good because I wanted you guys to see like a different method of this. A little bit of a review from grade 10. So -14 plus 20 is 6. -4 minus 2t is -6t. So I get 6t equals 6, t equals 1. So that's one parameter. And then we have already isolated for this s. So go ahead and substitute the t into this equation for s. And I get s equals 4. Okay, just changing color. Okay, so we have s equals 4, t equals 1. So what we're going to do now is we're going to substitute the 4 and the t back into both of these sets of parametric equations, and we're going to see if we get the same points for both. Okay, so here's the thing. Because we did substitution or elimination, like we found the points of intersection of these two lines right here when we equated them, what I would do is I would actually start off with doing like the third. Because no matter what, the x and the y are going to work. We made them work by doing substitution or elimination. So let's go ahead and start off with the z. So z equals 6 plus 5, and then what's s? 4. 6 plus 20. So we get 26. And then we get z equals 30 minus 5t, which is 1. 30 minus 5, I get 25. So these two are not equal, therefore there's no point of intersection. Therefore, no point of intersection. These lines are askew. Okay, and just to recap, we know that they're not parallel because D1 was 1, 4, and 5. And D2 was -1, 2, and -5. So D1 is not a multiple of D2. So we knew that they weren't parallel or coincident where they lie on top of one another, so they are indeed skew.